So we have basically go for the elementary, say the elements, the basic elements of a neural networks. So we whenever we have a network, essentially it's just trying to, I don't know why this, let me pull this up. Yeah, okay. Essentially like training a network. Okay, the procedure will be like you design the architecture of your networks, and then afterward like you want to prepare your training data, and then like the training is just essentially just you put in the training data, you just full backpop, you find the gradient. Actually most of this of course will be done automatically if you implement it like with packages like PyTorch and TensorFlow. Um, and then optimization will be more or less automatic also. Like you determine like what kind of like optimization you want to do. Like either you want to, for example, like atom or like simply stochastic gradient descent with or without momentum and so on. So like today we're going to start to talk about like different architectures of neural networks beyond just simply a fully connected layer or fully connected neural networks that we have like each of the layer, then I have another layer, then we just connect everything. Like that's basically what we have for the moment. And then you may have multiple layers and so on, right? I probably will make up an other homework, just do something simple as that and continue to do um, trying to tackle the same problem like as the previous homeworks to just to do a regression, but maybe you do a neural network regression. But okay, so now go beyond of this fully connected layer. So the first thing we like to talk about is CNN, the convolutional neural network. Uh, actually, CNN or CCN, CNN. So and the convolution basically is like um, just borrow the terminology from cell processing, image processing. So the idea is pretty simple. So if you think of like, okay, the problem of classic neural network when you have like fully connected layer. Let's say let's work on images. Let's say like a simple image, like small image, as maybe just say 200 by 200. Now, I if I do a fully connected layer for like several layers, so for 200 by 200, then I will have what like one layer. Let's say the input here, the dimension will be like just 40,000, right? So just the number of input pixel. Let's say in the next layer, I also have a fully connected layer. Now, what's the number of parameters here? So maybe I just a warm up. Like how many parameters do you have? Like if I have a fully connected layer in the next layer, let's say I also have like 40,000 uh, kind of variables here. Yes, approximately like yeah 40,000 square, yeah, approximately if you count the bias then maybe 40,000 square and also like 40,000, but anyway like that's close enough. But you can see it's like it's huge, right? So this is approximately what is like 400 million, I guess. Wait, 40,000 is like, sorry, 16 million. 16 million is like 1.6 trillion already, is that billion? Yeah, not trillion, yes, 1.6 billion already. So even you have an image, this is a not a very high definition as high resolution at all. Uh, but you already have like just one layer of like fully connected layer. You can have like lots of variables. So it's not realistic in practice. So the idea of convolution is just couple whatever like people in image processing and computation. So if we think of like you have an image, like whatever I have image, if I think of like pixel in an image, so the pixel, like a particular target pixel, it should not have like too much correlation with pixels like far away from its neighborhoods, right? So for example, if I want to process uh, this pixel somehow, maybe I only need to consider like the neighborhood of this pixel, right? So I don't really need to like care about like how this, I mean, have kind of like consider like inputs that's far away from this one. For example, I don't care about like what's the value for a pixel like far away like here. So then in the sense we can think of, okay, if I want to do a lowest uh, level of like processing for the label of this pixel, I may just do a filter. In the sense I filter, which means that just say I take a patch of this one and I do an inner product of a filter of like same size. So this is a some kind of filter here. Then after I do a dot product, I will get some value, right? Then the value will be the value for this pixel here. So and I can have multiple filters as well. Like I can, this is like filter one, maybe I have filter two here. Okay, I want to draw it more or less the same size here, right? And I have like filter three and so on and so forth. And then like each of them will be just do a dot product with this guy. So compare with like, say a fully connected layer here, like if I have fully connected layer of 40,000. So say if I have a filter size is 5 by 5 here. So um now the point is like I also like kind of assume something is like kind of translational invariance in the sense like I I I will assume that like the filter to process like places like for example the upper corner here uh should be kind of the same as the filter like process the lower corner here. So anyway, like it seems reasonable, right? Because I without any further information, of course you can make adaptive filter that will be difficult, like, but this will be a reasonable assumption, just assuming that like for the entire image, I'm going to use the same filter. And this is just basically classic image processing or like computer vision doing like uh, uh, a finite length or like finite size filter. So a finite kernel filter. So now the only difference like for CNN is that like I will have the the filter now will be trainable, right? So in classic signal processing, classic image processing, we'll just design this filter. Let's say I have like this is like some of this Gabor filter or like wavelet filter and so on and so forth. But here, I don't know, it'll be data driven. We give the data for whatever task we are kind of like aiming for, maybe doing classification and so on. So we can adjust this filter as well. So this filter will be just also like controlled by some parameter, right? So in the sense like you can think of the filter now. For example, like I have this 40,000 kind of like uh, coefficients here, like for the image, pixels for the image. Now, if I have a 5 by 5 filters, I will have like taking like 25 of these coefficients here. I will weight the sum together, right, to get the next output. So something like, okay, the next output for this one, maybe just this guy here. It won't be consecutive like this because yeah. So, but anyway, for simplicity, let me just draw like this. And then like I weighted some, these 25 of them, and the weights here will be controllable, like I mean, trainable, just as before, right? Um, and what else? And also like I can have multiple layer of filter. So let's say like I have this is like my uh, first layer with the corresponding like filter one, right? As I mentioned, then I have another layer I correspond to filter two and so on. Now then I if I have like let's say k filters here. Now after the doing the k filters, I can kind of put all this like filtered output together into a three-dimensional block, right? So I can have like the original image would be start with like, let's say is let me draw like this. I say 200 by 200. Let's say it's just grayscale. I have only one channel here. So after K filter, I approximately also have the image like have like the output. Let's say it's like 200 by 200, ignoring the boundary condition. We can do some padding and so on. So if I have a K filter, then will be a three-dimensional structure with like 200 by 200 by K, right? Now in the next filter, now we can apply the filter. This is the part that is also differentiate from kind of deviate from classic image processing. For classic image processing, we more or less apply the filter only at one channel of the image. But in CNN, after this first level of CNN layer, convolutional layer, we have this like three-dimensional block of like K by 200 by 200. We'll apply now the filter, like for example, if I apply a filter, like maybe like again a filter size of 5 by 5, then usually people say it's a filter size by 5 by 5, but the actual dimension of the filter should be like 5 by 5 by the number of channel of the input. So this is like the channel of the input, okay? Number of channel of the input for this second layer here. So then like you essentially have the filter size. Okay, my drawing, my writing is a little bit not legible. So it's like 5 by 5 by C here. Now then again, I have this three-dimensional here. It's like 5 by C here. I have this block. So this filter, again, like this filter coefficient will be trainable. This can be like, so for the next output, then will be, again, like I will take this block here, do a dot product, maybe different colors here. This block here, do a dot product if like this block here. And of course, like this will be like corresponding to just coefficient here. Then for the next coefficient, I will have this block now. Maybe like if I want to do a dot product, okay, consider coefficient, filter value of this coefficient, then will be this block, do a dot product with like, let's say this block here. So it's something pretty straightforward. The idea of CNN is actually very straightforward. And let me maybe go for some slides here upon. So just illustrate that. So this give an example. Let's say I have the image here, like start with an image, say 32 by 32 by 3. So that's is like now it's like three, it's like have like 3 color channels, let's say. And now if I have filter like 5 by 5, let's say, and usually people just say the filter size is 5 by 5, but it's assumed that like that will be like actually it's like 5 by 5 by the number of channel of the input. So in this case, 3 here. So then like you kind of do a dot product, right? Let's say if I want to find the output value at this pixel, so we'll be just takes this block, get it out, and then do a dot product with that filter. So then we will get one number, right? And then like, so if I go through the entire image, let's say here, I'm assuming no padding. Like if I have no padding, like I have my filter size is 5 by 5. So then I cannot start with this pixel, right? Because like this value here is unknown. So this value is not, I'm not sure about like what's this value here. Or then maybe I draw it like in this, like from this seen from this view here at 32 by 32, right? So this pixel, I cannot compute the value for that one, right? I cannot compute here because I don't know values here. So the first value I can compute will be like somewhere here, right? So it's like if 5 by 5, actually it's not drawing very well, but anyway, so therefore, like I will, if I have no padding, like each dimension, each size here across the boundary, I need to minus 2 here, right? Because my filter is like 5 by 5. Okay, let me wait. right? 5 by 5. It's hard to, yeah. So what I mean is I need to start with, if I this is index is 0 0 here, so I need to at least start here, like 2 2 here, right? So and so therefore, like you see, like for the boundary here, like this is the place that I cannot compute. So therefore, like of course, for each of the boundary will be for a 5 by 5 filter, I will have like reduce the size by 2, basically, I want to say. So therefore, like the final size of the output will be just like 24 by 28 by 28. And with one filter, then I have like 28 by 28 by 1, there will be one channel. If I have another filter, then it will be like, let's say, one more. If I have, let's say, 6 filters, then I have the final output dimension will be 28 by 28 by 6, right? So this is a illustration that, let's say, if I go for one curve layer with 6 filters here and like 5 by 5 by 3, there's no padding, then I will have like 28 by 20 by 6. If I do it again, like no padding, let's say if I have like 10 filters, I have something like that, right? So that basically it. So um, maybe just test your understanding. So it's like so obvious though. So how about if I have like this filter size is 7 by 7 by 3 or 7 by 7, let's say. And let's say I have like uh, 10 filters here. What's the dimension of this output here? Assuming no padding. No padding. Yes, yes, yes. Yeah, very, very simple. Right? So you have, if you are 7 by 7, then like, if you don't pad, then the boundary will reduce by, reduce the size uh, by what? By 3, right? So then each size reduced by 3, then reduced by 6. Okay, I'm not sure you guys are correct. Yeah, yeah, you're correct. So it'll be like 26 by 26, and my 10 filters will be 26 by 26 by 10. Yes. And usually you can pad whatever you want, right? You can pad, for example, like typically, uh, if you don't want to have the size shrink, then I can pad some zeros at the boundary. So let's say if I start with 32 by 32 here. So if my filter, like again, is a 7 by 7, I know I need, if I don't pad, I will shrink by 3 here. So therefore I can pad say uh, 3 columns of zero, right, on both left and right, and also like 3 rows of zero for up and bottom. So then in that case, I will get back the dimension is like 32 by 32. So um, it's all very simple, like and natural. So that's padding, and also like uh, there's another terminology that you probably already know, like if you have worked on a little bit CNN. Oh, actually, that is a participation question. I just want to know, uh, how many of you like have played with CNN before, like CNN, like in any way? For example, like using Keras, PyTorch, I mean, like implement a little bit CNN or something. Like I think at least a couple of you did. Yeah. So yeah, yes and no question. Yes or no question. Yeah. Can yes. Okay. So I have some idea like how many of you have no more. So I don't know. Okay. Yes. Um. So okay, but let okay, but right now I think everything is very simple. Right? So there's nothing really magical. Um, but you see, like, okay, maybe do a little bit counting here. So get back to the original example. Like if we have like 200 by 200 size of the image, maybe just one channel to start with. Now we said that if I have a fully connected layer, let's say I have the next layer with like also like same dimension 200 by 200, that's basically 40,000 here. So the number of parameters here will be like 40,000 square, right? Approximately. So now, if I use a CNN here, like let's say Q question 2, question whatever number here, let's say a CNN with a filter size of 5 by 5, let's say. Now, how many parameters do I have like for this conv layer here? Number of parameters. So at the beginning, one layer is like 200 by 200 by let's make it a bit not exactly I say challenging, but like let's say the output have like 10, maybe 6 layer, like just 6 layer is that. So I have like 6 filters here. So how many parameters for this conv layer here? Number of parameter of this conv layer. So is my question clear? Let us start with I start with I start with an input image, just as a one image here, say 200 by 200. Now after I the output now will be like 6 channel. Like you can also think of like basically maybe I draw it in like similar to here, like will be a block like this way with like 6 channel here, and the height and like the dimension along this here will be again like 200 by 200. So now I have some conv layer, a conv layer that from here to here, and the conv layer, the conv filter here I use is a let's say 5 by 5 the size. So now how many parameters you can count, right? You can count like get a be careful. It's number of parameters, not number of coefficients. You guys need to differentiate the difference. More than that, like yeah. So think of what are the parameters here, right? So the parameter think of like okay, I have the parameters is actually the filter, right? So I have the filter. Unlike the classical case, the filter is predetermined. Here, the filter is trainable, and you can vary it. That are the parameters, and you have like in this case, like if I draw it here, so it would be like a block, right? That would be a filter. That block is going to do a dot product with that. Yes, yeah. So you have that block will be have a dimension simply like 5 by 5, but know that I have like six output here, 6 per pixel. So therefore, like I have 5 by 5 by 6, right? So for each of these channel here will be 5 by 5, but I remember you have 5 by 5 by 6. So you see, it's like a major reduction here, right? So if you had a fully connected layer, it would be huge. I don't even care like what was exact value, but it's a many order of magnitude. And that's is important because you have too many parameters that is difficult to train and expensive, right? So and that's also like that's why CNN is so powerful, or like you can think of that. It's just leverage some of the structure of your data, saying that okay, if I have pixel here, it's not going to relate much with pixel here. So therefore it's reasonable I have a finite size filter here. Yeah. So I guess maybe I have a related question, just see if uh let's say if I remember, okay, remember for example, like in your homework problem, like we are trying to do regression with some stock data, right? So now let's say if I have the stock input, let's say like here, of course, I'm showing this 2D CNN, right? But I definitely can use, I mean, kind of extend or like uh, degenerate this idea to whatever like lower dimension, let's say 1D or like extend to like 3D, 4D, and so on, right? So just your filter here will be like a higher dimension or lower dimension filters block. Essentially, you still like have a block of data, a tensor, a block of tensor. You're going to do a inner product of this block tensor with the a part of the your data here, data there. So for example, if I have 1D, let's say if I have 1D, I can do CNN as well. So if I have 1D, uh, I can have this is like let's say 1D data is just as X here. I can have filter F, let's say, right? So I have this filter, just for example, if I filter, let's say this X, maybe I give a concrete dimension for that this guy. Maybe like I have 10 samples here. Maybe, yeah, let's say 10 samples. Let's say, okay, let's say if I have a filter of a dimension, like here is a length of like uh 3 here, of yeah, 3 here, let's say. Just think of 3. Okay, a 3 coefficient here. Okay, maybe like another question, I just simple question, I think. Uh what's the output of this? What's the dimension of the output, let's say, after this filter? I assume no padding. No padding. So I have input dimension is X is just a length of 10, filter length is 3, no padding was the output dimension, just a single filter here. Yes. Yeah, very simple question. It's just 8. Yes. Um, Now this is actually a more interesting question now. So let's say if you remember, like we did in the homework, like trying to do regression, right? Maybe I can have one-dimensional data. I just think of like different days to be independent. So I have input, like for example, like I'm trying to predict the current day's price, how Tesla, maybe like the stock price of Tesla, is related to like other stock. Maybe like that's like maybe that's Microsoft, and then maybe like that's Intel, and maybe like that's like Nvidia, yeah, and so on and so forth. So I have like a bunch of stock symbols, and then like basically I'm just doing a prediction. Of course, like this is a let's say uh let's say I try okay let me okay use another place to draw. Like I guess I just draw. So what I mean is like let's say I can think of okay, try to do a stock prediction again. So I have an input. Let's say I have different stock price here. Right? So the input is like different stock price here. So let's say I have like the first one maybe like Apple, uh, and then maybe have like Microsoft, maybe that's Intel, right? And maybe I want to predict Tesla price eventually. I have Tesla here. So maybe I can have like multi-layer neural network. Maybe like initially I do some conv layer first, and eventually I do uh, a fully connected layer. So let's say the final layer is fully connected layer. Now I have like intermediate layer. Let's say this is a somehow like I do a conv flat here. Of course, I can do fully connected layer, but I say like, okay, well, I want to reduce the dimension, so therefore I do a conv layer here. So this is a conv layer. So my conv layer maybe have a filter length of like 5, let's say 5, let's say. So it will be something like, then therefore like essentially like this first value here maybe like assume no padding again. So no padding. So it would be something like, okay, maybe I draw like a little bit better. I think if I use this, will draw a bit better. Yeah. So something like this, right? So so therefore like this coefficient, therefore like maybe like the first 5 here, right? And then the second coefficient, oops, maybe the second 5 here, right? Okay, like that and so on. Okay, now my question is like, so is it a good structure? Is it a good architecture? So mainly, my question is like, is this conf layer is do you think it's this a, it will give you good result if like I use a conf layer here? Like is that a good choice or something like? Yes. I want to put that point here. So we have this assumption we can have conv that work for images and so on. It's because you have this correlation structure, right? So you expect like one pixel will be more correlated with like the neighboring pixel, but not correlated much with like faraway pixels here. So you cannot apply stuff like that to arbitrary data structure. For example, like if I have stock price here, I'm not somehow I don't know how you kind of like pre-process like to create a stock price that are order in the sense they have some kind of like correlation structure that imitate this. Okay, in general, it's not possible. Also, in general, it doesn't make sense in any way because like you don't expect the filter to be um, invariant because I if I apply that to let's say Apple, Microsoft here, um, I I have some other stock here, right? Maybe I have like some bank stock, like maybe like City or something like that. You don't expect like this guys is going to have similar kind of like the filter should, I mean, like the data itself, like you don't expect like a similar filter should be used like for the bank data versus with the tech stock. So you expect like the filter properties will be different. Unlike for an image in general, because like images like you expect shift environment, right? Because you take a photo here, you let's say take a photo of some image, if like someone take the okay, I'm trying to draw a camera, definitely doesn't look like a camera. So and if you shift a little bit the camera view, so you will take a photo, essentially take a photo that is a scene with a shifted view, right? So in by nature, images are shift invariant basically, but by nature, like for this kind of data, it's not shift invariant. So yeah, it doesn't make sense. So it's like kind of like be careful like where you can apply conf filter, conf layer. So okay, that's just a remark. Let's see. Like let me see. Like maybe it's better to uh oh where's my okay. Um oops. What did I click? So that's for stripe and padding. Okay, next thing supposed to talk about is polling. I guess I um the idea is very simple. It's like, let's see if I should show it in the slides or like easier to talk about that like by drawing. Um, my slides are pretty good. I guess I'll just uh, fully connected layer. Yeah, probably be. But okay, this is pretty confusing. Like when you say FCN, unfortunately, like people like to refer FCN with this fully convolutional neural network. I don't know. Uh, for so yes. That's pretty confusing. This is pretty unfortunate. I also like yeah, find that very confusing. So but when people say, I guess you can just ask him like what does he mean by FCN? Like when people say FCN, because that's some work, like I probably will mention that also, like they basically eliminate the fully connected layer and call the network fully convolutional network, and like shorthand with like a symbol like that. So yes, but if you can't kind of trying to deal with data doesn't have special spatial structure, then you should yeah okay, of course, like later on we will talk about attention network as well. So another option is to do attention network. It's become very fashionable nowadays. So you have an attention model, and then like uh yeah, we will go into that like later on. Yeah. So and so for polling, I guess I'll just use the slides here. So let's see if anything interesting to talk about. Yeah, I guess I mentioned that in the past, right? So you can think of like lower layer. So even though like not everyone agree with this anymore, like for example, like I listened to an interview of Goodfellow, and he doesn't think of this way anymore. So, but like I guess high level, like maybe you explain to some layman people level study like neural network before, is still like a powerful analogy. Um, powerful metaphor is like you can think of the lower layer as a generate trying to at least trying to generate lower level features, and then like in a higher level layer you're going to extract like more complex features. um and let's go to the polling here. Where's that? Yeah, polling. So now the polling layer is like very simple. It's just trying to downsample the images, the image. So it because I the idea is a yeah, it's hard to say like okay. Of course, when you do downsample, mostly it's like for reducing the number of parameters. Honestly, I would say that many of these operations is a little bit ad hoc. I guess it's like more like arts than like there's like very rigorous science to say why I should do polling here and why doing polling versus not doing polling will be better. But this is like a convention that many people do, like when they want to reduce the dimension of the image, and they apply polling will be simply like you have like the input like this is like 4 by 4. Then I will just take like, for example, if I have like polling by like a 2 by 2 filter here, then I will just say take 2 by 2 block, and then I just take the maximum value of them. That would be the most commonly popular mass polling. And I forgot to mention stride also. Like stride is just saying that like how much coefficient you're going to skip. So typically when you do polling, you for example a filter of 2 by 2, you stride by 2. So meaning that I will take the maximum of this 4 block to get this value here, and then I skip one coefficient, so therefore go to here, and then I take a maximum of this. I have 8 here. So maybe just to see whether like you actually following what I'm doing here. Maybe not very complicated exercise, but exercise you may take a minute or two to figure out, I guess maybe. How about a two by two? Let's see. Then maybe like 3 by 3, like 3 by 3 polling with strike one. So what would be the output for that? Yeah, it's just the dimension is 2 by 2. Uh, how about the actual values? Maybe evaluate the actual value. Uh, yes, yes, some of you got the 8. So yes, yeah. So if I do 3 by 3 polling strike one, it means that okay, the first coefficient will be taking maximum of this block here, right? So the maximum of this block will be 7, and then for the next coefficient here, will be like just taking the maximum of this one, so it'll be 8, and then trying to take the maximum of this one with 7, maximum of this one would be 8, something like that. So 7 is 7, 8. Yeah. So there's mass polling and strike and padding. So of course, like for strike here, I can also use it for conf layer, right? So by default, typically we have like a conf layer assume strike one, but I can do a strike two as well, right? For example, like I can do a conf. Uh, so let's say okay, I don't think it'll be too bad. So how about I can do another exercise? Maybe I have a filter like this. Maybe I just do like this 1 1 1, and then I also here, and I do a conf. This is like a conf filter to a convolution with this guy with strike two, and this time do padding like padding. So padding of one on each of the boundary. So what will I get?
Um,
Yeah.
could you repeat the question maybe from the
Oh, okay.
beginning?
Yeah. Okay, I have the filter like this, like conf. This is the filter, so a 3 by 3 filter. Apply on this one here,
Okay.
and let's say I do a padding of one. So that means I padding one. I mean, across each of the boundary here, like I will pad a column or like a row of zeros, and strike two, have strike two. So it means that like we will every time after doing one filter for a particular coefficient, um we're going to skip like two. Uh, so like if it's strike one, we'll kind of process each of the coefficient. Right? For strike two, if I work on this one, then we skip this one. Right? I will skip to this one. Right? And then vertically is also like if I have strike one, I will try to work on this one, but if strike two, I will work on this one. Right? Something like that. Yeah, some of you get some values, different values. Yeah, three values. So yeah. So anyone are still working on that? Maybe I'll, take some water and let's see. So let's see. So if I have padding padding is one, then I would just pad one row or columns of zero, right, across on off each of the boundaries, right? So I have like zeros here, right? And then the first so my filter is 3 by 3. So the first coefficient I can work on is this one, right? So then I will say get 6, right? So this add this, add this, add this, I will get 6. So I will get 6 here. So then the next one is try 2, right? So I skip 2, I will skip to here, right? So here I will also like, okay, sum over what? Do a dot product of this guy. I have like this one, add this one, this one. So it's a what's that, 12, I guess. So then I try to work on this guy, right? So okay, note that I cannot work on this one now because I have only padding 1, so I don't have anything here. It's undefined. So and for this one here, I have this guy, so it will be this, some this, so it will be 8, and then this one, last one, this one, some this is 12, yeah, something like that. So okay, so some got it correct, some got okay. So I'm not sure it's a numerical problem. So anyway, so let's see. Let me see what I okay. So then maybe let me just show you a typical and very classic classic CNN. So typically we'll have a structure like this. So a typical CNN, like even though this is a more classic architecture, now have lots of variation. Especially, we'll talk about, for example, like um, special module, for example, the Inception module like by Google, and also WestNet, the WestNet module like by Microsoft. Um, but like the general one, or the most basic one, for example, you think of AlexNet or like LULET, have similar structure. Is that you start with like some conv layer here, like some conv layers, and after conv layer you have the activation function, for example, using value. Um, that's actually that's I guess uh that is one contribution. I'm yeah, I'm not 100% sure. Like maybe some guys to correct me if I'm wrong. I guess I for Lulat 5 is already using Velut. Yeah, and this is a for by Lacoon, like in 90s, I trying to do digital recognition, like hand what's that, handwritten digital recognition. Uh, and so like Lula 5 has a pretty much similar architecture like this one already. So we have like some conflat, and then like activation, yeah, activation, and then after a while like conflat activation and so on, then maybe do some polling, and then conflat activation and so on, like polling and so on and so forth. And finally, like typically we'll have some fully connected layer. So usually have some fully connected layer like this. And then like from the full, then afterward, let's say if I doing classification, then maybe I have like, uh, maybe like I have like 100 classes. So then the last layer, I will have like 100 coefficients here, right? So then like this last layer, like will be kind of like trying to fully connect it to these 100 coefficients here. Then this event should give you the score, right? So then you can, this score can go through a kind of softmax layer just normalize into probability, then like say in this case would be like, okay, the coefficient correspond to the car, maybe like have a highest probability, then like will be classified as a car. Um and okay, I'm just grabbing like this is the roulette architecture. So for the roulette architecture, like as I said, like it's very similar to this kind of basic architecture here. Right? So we have conv and then have this is a subsampling is a basically polling, and then like conv polling again. So actually you can and then finally you finally have like several fully connected layer. I'm not quite sure this Gaussian connection. I forgot like on top of my head. I don't know what is that honestly. Um, but probably not very important. Some of these architecture, like for example, like in AlexNet, like they have this special kind of normalization method that is actually become obsolete because people find that it's actually not useful. Like they kind of like put that in the original architecture and and thought that like, it's useful, but then eventually people find that it's not useful. So uh, and yeah, this Gaussian connection is probably not important because I don't quite uh, yeah see that like in somewhere else. So this is the roulette and roulette 5 back in so this is maybe too small.
Dr. Cheng,
Yes,
this subsampling operation,
yes.
is that just a pooling of some kind, or?
Yeah, it should be just pooling, but the thing is like yeah, it's a pooling of some kind.
Okay,
So, but I'm not exactly sure it's mass pooling though.
could be something
But
else.
it could be just average pooling.
Yeah.
Yeah. Yeah, you can do average pooling as well. So I'm not so it's just like I'm not exactly sure the activation is valid. It can be yeah, I'm not good historian basically. Yeah. Yeah, I need to dig up back to the paper. But the architecture is like more or less very much like this like classic architecture. So basically. So and another like classic example that you at least you should know of like kind of is AlexNet. So this is like historically it's very important because like this is the winner for the 2012 like uh, image like competition that basically changed the entire field, like get all the researcher into the neural electric cam basically. Um, and you can see, okay, this is like the architecture itself. Like now you look at it, it's a little bit funny because it's split into like two kind of uh, two branches here, but it's mostly because of historical reason because like he trying to train on GPUs. Like he is kind of like a uh, very much like the first couple people like trying to train like lecturers in GPU, and GPU at that time doesn't have lots of memory, so he is forced to like split the models into like several pieces to train them separately, and then every once in a while just exchange the coefficient and so on, so make it like it looks like pretty complicated. But other than that, like nowadays people can just put everything back into like just uh like one kind of like one uh, sequence of like kind of streamlined model and works well. And AlexNet and don't have anything particular. Let's see that. Yeah, as I mentioned, I have some normalization layer, but it's not used anymore nowadays. Um, and another architecture that like to mention, at least I briefly mentioned, is VGGNet. So because these are the names I'm giving. I'm kind of like basically mentioning names that like you will come across that people are still using. For example, like nowadays you maybe less now, but still you will see like people like use VGGNet. Maybe I don't know for just a trial, I guess. Because I guess there are a lot of like quite well implemented version, like implementation for VGGNet that people can just still like modify easily. So therefore, like it's kind of like popular. Um, at least it was popular. I don't know. I didn't keep track of like how the recent papers go. So, but at least I kind of uh review a book proposal like a couple of weeks ago, and then like the book proposal like have like multiple sessions and chapters just saying that like using VGGNet for blah 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 and using AlexNet for blah 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 and so on. But I to be honest, like that was a really bad book. I can't like saying that like it should never been published. But anyway, um, yeah. So okay, I'm kind of digressing too far. I'm sorry about that. For VGGNet, like I guess the main thing like to a main contribution is like they realize that smaller filters is like better than larger filters. In the sense that, for example, if you think of a 5 by 5 filters, you can totally replace by 2 layer of 3 by 3 filters. Because if you think of the receptive field here, for example, you think of a pixel, original pixel, like original coefficient, let's say like this one here, let's say after 2 layer of 3 by 3 here, how maybe like this 3 by 3, 3 by 3. Now let's say I have like this is the output. I have this output value for this one. So if you think of like what coefficient actually of the original image influence this output here, it will be like 5 by 5, right? You agree with that, right? Because I for this one here for the this next layer here, okay, here I'm not drawing 5 by 5. Now it's 5 by 5, right? So because if you think of like uh for the input that will affect like this one here, like for the previous layer, the one that at this corner will be affected this one, right? But which one, the original layer, original input will affect this one will be like can be uh like this one, right? Like basically 2 pixels away from the original value here. So therefore, like effectively, you can think of this 3 by 5, sorry, 2 3 by 3 layer, conv layer can can become, or like you can think of like a 5 by 5 layer can be modeled by 2 3 by 3 layers. So you will say like, okay, what's the big deal about that? Like, why want to do that? So if if you think of like multiple of these layer, for example, I have like 11 by 11, so it can be replaced by like maybe just 7 by 7. It can be replaced by, in this case, it would be like 3 layers of 3 by 3, right? So then like 3 layers of 3 by 3 will be like 27 coefficients, right? So but 7 by 7 will be like 49. So you will have like some reduction, even though it's not as much of reduction of parameters as like um, from fully connected layer to complex, but you still like get some reduction. And it's like significant reduction, right? So you have like um 60, 60, 70% maybe here, like reduction of number of coefficients. Uh, so and that can contribute to some reasonable gain there. Um, and
Do you lose anything though by having smaller filters?
you lose flexibility definitely, but in terms of performance, you don't lose much. Uh, Actually, the trend is still like you often don't go to like large filter. With some exception, for example, like for Inception module, you have like several of like different filter size there, and then like they merge them together. Um, but if you just use one filter here, like it looks like people like always do it's always almost always get like better performance, just reduce the filter size, give
Okay.
more layer and then reduce the filter size. I'm not sure you can go extreme, you can go one by one filter, right? One by one filter doesn't make sense for classic image
Yeah, I've
processing.
seen that. I
Yeah,
it's always confused me.
so but it makes sense because you think of like, okay, the for CNN, you as I mentioned earlier, for CNN, it's different from image processing, that we don't take a channel like for classic image processing. Actually, we take a channel here at the time I'm doing the filtering, right? So for example, if I have like 20 channels here, typical what we mean is like for each of channel, like we have a different filter. When you have filters, like for example, I have 5 by 5 filters, then I will take the first channel, like take this layer here, and take this one, do a dot product with this 5 by 5 filters here. But for CNN, it's different, right? We actually take the entire three-dimensional data block to do the inner product, right? So therefore, in this sense, for example, I have 40 channels. In practice, I really take this 5 by 5 by 20 box here and dot product with this again, like the filter also have the size 5 by 5 by 20, right? And this will give me actually one layer only, right? It will give me one layer of input, right? So I get one layer here. And maybe I have like 6 of this filter here, then I have like 6 layers here, right? So now, so therefore, like for classic image processing and computation, it doesn't make sense of one by one filter because like one by one would be just scalar one value, right? It just says take multiply the layer, entire layer by a scale value. It doesn't change anything in practice. So, but if you do CNN, you are actually, when I do one by one layer, or sorry, one by one filter, what it means is actually multiply this thing here. For example, like if I do a filter on this coefficient, I'm multiplying this with this one, this this column here, right? So I extract this column here, do a dot product with this column, right? So I
Oh,
give one value here.
yes.
Yes. So and I can do like multiple filters again if I have 6 of these columns. Like essentially, I have like 6. Okay, I cannot draw it. Yeah. Okay. Anyway, 6 of them. Let's say like I have 2 more, and and I will have like kind of like from this block here, original like maybe for dimension 100 by 100 by 20 into this like 100 by 6, something like that.
Okay.
And you see, like typically people use it as a compression, right? So you start with like many channels here, like channels and maybe 20 of them. You of course you can do the other way one as expansion as well. So you have the output now is like reduce the dimension to like 100 by 100 by 6. Um, and you can combine this, like for example, like I can do a, for example, I can do a filter. So what I can do is I can start with this dimension is 100 by 100 by 20, right? Now I can do a reduction here, one by one filter, 6 of the one by one filter to get like 100 by 100 by 6, let's say. Now here I do the 3 by 3 filters now. And I will get maybe like again 100 by 100 by 6. Let's say I also have 6 filters of them. And then like I expand that again. Like now I expand, like I have like 20 by 1 by 1 to have like 100 by 100 by 20. So I have an operation that um, essentially is similar to doing a 20 by 20 by 6 by 6 filter here. But if you count the number of parameters, you will reduce the number of parameters. This is like effectively like this here. But if you count that, what is the number of parameters here? That will be like 36 times 20 will be like 620, right? So number of parameters here will be like uh wait, actually I need to multiply by 20 as well because it's a out input is 20 by 20. So times 20, let's say. So here will be like 6 here, and this is a 6 times 9 here, it will be 54, I guess. So this one is a 20 here. So you have like 6 plus 54 plus 20. I need to multiply by 20 again. So, but you see, this will be what? Less than 100, right? So this is much less than this one, like 720.
Okay.
Yeah. So yes. So I'm jumping ahead. Like I will repeat this. So, but this is a using smaller filters help. Even though like actually when I talk about this VGGNet here, let's see, maybe I jump to the slides again. Um, so this is the VGGNet they use, the architecture they use. It's hard to read. So you see like they use lots of these 3x3 filters here. So this is AlexNet. They use this 5x5 and 11x11. They more or less replace that. They try a lot of combination, and then see that like find that like they get better off like using like smaller filters. So essentially they only use 3x3, but they didn't use like 1x1. And this is VGGNet and then like later on like Google, they have so-called GoogleNet like in 2014. So the main thing is that they introduced this known as this Inception module. So maybe I have let's see, do I have a yeah, maybe this Inception module is like this. So it's basically like you try to like go for it's just in parallel. You cascade stuff like in parallel. So you have like this one by one conf, right? Conflat, and then 3x3 conflat, 5x5 conflat, and then each of them you cascade together. So one by one conflat, you well, I mean like you go for this guy here, you will have like some, for example, let me make it specific. Let's say I have like this have like uh two filter one by one. I have like two filter 3x3 and two filter 5x5 here. So each of them I get two layers here, right? So let's say I have this original image is a 100 by 100 again, right? So I have like I assume all have padding. So one by one here, like the output will be like 100 by 100 by 10, 2, let's say, with like two one by one filters, and then like and then I have like 3x3 here. I do the same thing, right? If I have two filters, I have like two 100 by 100, right? And then I have like also like this guy of 5x5 also have like same dimension, like 100 by 100 by 2. I'm actually I don't need this to be like 2, 2, 2, or maybe like I have this one here, maybe 4, maybe something like this at 4 of them. So then you just kind of like pad them together, cascade them together. So if I only consider these three together, so therefore it will be like 100 by 100 by 8, right? I have a block like this. And I can also combine polling here. The polling, if I do, let's see. Okay, for this polling, it's not going to use strike 1. So typically you do polling, you will have polling strike 3, right? So here will be like polling strike 1, also like with padding. So therefore the dimension again is also 100 by 100. So then I also can add a polling layer. So then eventually I will have together, if I have example 2, 2, 4 here, I probably have like the number of channels now will be 9, something like that. So this is like the naive implementation for the Inception layer. But then of course like, they can use this one by one trick there, right? One by one conf layer here. So as I mentioned earlier, we can do the compression. Let's say I start with this block here, maybe like again it's 100 by 100 by 20 channels here, right? So I want to shrink it a little bit. Maybe I shrink it to maybe it's like just 100 by 100 by 3. Then I can reduce the number of the coefficients here. number of parameters here. So yeah, similarly, I can do one 5 by 5 also. And for mass polling, like if I have 20 layers here, I can also do like, if I just do mass polling on 20 layers, then I will have like 20 channels as well, right? 20 channels output here also. But I can also do a compression here to reduce the size here. So I get like, okay, I guess I here, maybe I just give some concrete question here. So maybe like you guys, make sure you guys are following. So let's say I have the original input. Let's say the dimension is like 100 by 100 by 20, right? So now let's say I have conv layer, I have conv filter here, say two filter here. And let's say here I have this one by one filters here, like have 6 filters here. And this have like 3 filters here. And then here have like 6 filters here. And then like 2 filters here. And then let's say like this conv here have like 2 filters here. So my question is like, what's the output dimension? Okay, it sounds, let me pull your chat here. So I guess like this will be a final question, and then I will just end here. What will be the output dimension of this so-called Inception module? Here I'm showing all I'm showing here is the filter size, and of course from the filter size you can figure out the other things. And this here is just 100 by 100 by 20. Let's say I have 20 channels. The dimension of the image is 100 by 100. And I might have padding everywhere. Full out, I have padding. And again, like this one have 2 filters. This guy have 6 filters. This guy have 3 filters. This guy have 6 filters. There's 2 filters. 2 filters here. So is the question clear? You guys are trying to figure that out now? Okay. Yes. Yeah. Yeah, I have this yeah, okay, of course this is reality, right? So you have lots of information. You need to figure out what is the information is needed. But precisely what is the output dimension? So you say 9. 9 is like what the so I guess I'm a little bit over time, but I guess so okay. Yeah. So actually, it's I know that it only depends on the output layer, right? Because um, yeah, I'm not trying to trick you guys, but this is reality, right? Because where in real world you also like get lots of information. No one will give you. I mean, for example, like hints that okay, this you should ignore that or like not ignore that, right? So I just give out all this information here, and some of this information, of course, is not relevant to this question here. So so you think of one layer at a time, right? So let's say if I have this is 100 by 100, I'm trying to, I only think of filter. So if I go for one by one filter, what's the dimension for this guy? So it'll be like 100 by 100 by 2, right? So I have two filters for this one. And for this guy, go for this filter. Here, the input here, the output for this one by one conv will be like 100 by 100 by 6, right? Now, but this conv here, when I go, I mean, go for this like 3 by 3 conv here, know that like the output dimension for this guy here is 100 by 100 by 3 here. So know that it does not depend on the dimension of this 6 here. So if you count the number of parameters of that filter, it will depend on the input. But if you think of the output dimension here, it should only depends on the number of filters, right? So it's 100 by 100 by 3. And similarly, like for this guy, the output dimension here is 100 by 100 by 2, right? And this guy is 100 by 100, wait a sec, yeah, 100 by 100 by 2 as well. So then the final output will be like you stack all these block together. So therefore it will be like 100 by 100. Then you have 2 plus 3 plus 2 plus 3, 2, then it will be like by 9, right? Yeah. So, okay, I guess that's it. Like any other questions, you make sure you kind of understand this, at least like in terms of dimensions, like.
Yeah, it makes sense now. I
Yeah.
just got tricked by the extra
Yeah,
information.
this can be very easily made as a midterm question. So therefore,
Okay.
sure you can. Yeah.
I have
So
kind of a basic question.
yes.
So what prevents the neural network from learning like duplicate filters? You know, is it just that that's a suboptimal solution, so it goes with something else, or?
I think like okay, I think it's actually uh to be honest, I'm quite sure they are really doing kind of like trial and error in terms of this give you good result. But one thing is that like if I only think of this operation, okay, I ignore these guys here. I just think of this add with these guys here. Apparently, adding this in parallel, like this one cannot be modeled by any filters alone. Basically, let's say if I have this thing here, let's say if I just replace this with like only 5 by 5 filters here, and this one cannot model this one, right? So I cannot have like a filter that actually absorb this one as well. But of course, if I just do, let's say, this 1 by 1, 3 by 3, and 5 by 5, that probably is silly because I can totally have like some of this 5 by 5. Let's say what I mean is like, let's say if I have like one filter of 1 by 1, one filter of 3 by 3, one filter of 5 by 5. I have one filter of 5 by 5 definitely is more general with like general than one filter of 3 by 3, right? So therefore, like I can have like 3 filters of 5 by 5 that will have a model that is will be more general, like 5 by 5 by 3. This will be more general than this guy, right? So maybe I use a notation like this, right? This will be more general than this guy, right? So but so therefore like this naive implementation, if I ignore this guy, this is a little bit more kind of silly. Um, but of course you can still argue because if you have like three filters, one is like five by five, the other is 3 by 3. Maybe the 3 by 3 is like uh have less number of parameters, so therefore less likely to be overfit. Uh, so you see, like there's some kind of loss of trade-off here. This is like not actually very easy to analyze, like why is better or worse. But you can only argue that like this model is more general than this model here. Like if I have 5 by 5 by 3, it's more general than this one. And this will be, on the other hand, it will be more general than like I only have one filter, 1 by 1, and then I have like 3 filters of that, right?
Right.
Uh, but why this one is actually better than like this and this? This will be like, actually, of course, it's not even. I should stop here saying like this one is we want to compare this one with this and this way, but actually we want to compare this one with this and this way. Compare this guy here. Now with this guy will be more tricky, right? Because we have this 1 by 1 filter trick here.
Yeah.
To reduce the number of parameters. But of course, like this 1 by 1 filter trick here, I'm combine this guy. This together should be still like is less general than like a 3 by 3 filters with 3 filters, right? So let's say, let me just write more clearly. So let's say I have used that example again. I have like 20, I have a 6 filter like for this guy here, and then 3 filters for this guy here, right? So it will be less general than just look at this block here. It will be less general than like 20 filters go with like uh 3 by 3, 3 times 3 by 3 to an output like this. But of course, like that would be a trade-off again. Like this is less general than this guy, but on the other hand, that for this one will have less parameters. So so I don't think I answer your question. I just give you
That's
more things
okay.
to think about.
Yeah. I
Yeah,
like thinking about this stuff, so I
this is
appreciate that.
yeah. I don't think like maybe there's some analysis paper, but I don't think those analysis paper is well known. At least not many people will come up and try to explain. Okay, is that this? It looks like this is all art. So eventually people
Yeah.
try that out and seems like okay, this work better this way.
Yeah, it's mostly empirical, right? People do the
Yeah.
testing and they say this works.
Yeah. So
Well, I do have a question that you definitely can't answer. I'm starting the homework a little late. I looked at it last night, and I'm looking through the paper that's associated with question 1,
okay.
and they've got the notation A star. Here, let me pull it up.
Yeah. Let me also maybe.
They've got XI or C, however you say that, star, and they got alpha star. And that's the complex conjugate, right? I just want to make sure because they don't specifically state that. But I can't think of anything else that would be.
Let me just make sure though. Let me pull out the. So the paper. Yeah,
Like,
that's the complex conjugate. Yes.
Okay, great. Thank you.
Yeah. Oh wait a second. Let me make sure. Wait a sec.
So
No. It's not. I'm sorry.
Okay.
I'm sorry. Right. It's just a different parameters actually.
Oh,
So they look at different directions here. So, you can think of that is the margin size. For example, like when this C here is a called C, I forgot. So it's like go beyond this boundary here. So if you look at this, like okay, the regression idea is like for the support vector regression is that we want everything is within here, right? If I won't have I have a hard constraint here. So if I have a soft constraint, then I may have some of these samples that go beyond that. So, and the magnitude that go beyond that is this C here. And basically like he have this C here, like okay, so C, why is it different variables now? Yeah, I think like yeah, it's supposed
the C
to be the same actually,
is related to the epsilon.
Yeah, it's actually like in the figure, it's just like not
by equation 4, I think,
yeah.
or something.
So, but the C here like will be yeah, will be kind of like in two different directions will be the same. So one direction will be like above, one will be below. So I'm not sure like which one is a star. So one of them will be star. Yeah, basically.
So it has nothing to do with complex.
Oh no, it has nothing to do with complex conjugate. Yeah.
Well, thank you for that. That helps.
Yeah. Okay. So any other questions? If not, then I will have that presentation next week. So I'll see you guys next week then.
Thank you, Professor.
Yeah, sure. Let's see.